Now that we know how to find maxima and minima of functions, we can work on some applied problems. Now, just as a reminder, there's some good ideas when you're working with applied problems. Certainly read the problem slowly and carefully, make sure you understand it. A good way to know if you understand it is to draw a picture and see if your picture makes sense. There are going to be some quantities that can change. You're trying to find the optimal choice here. So introduce variables to represent the things that you don't know, and try to write an equation of the unknown quantity, in particular the quantity you want to maximize. So ask yourself, what is it that I'm optimizing? Look for words that say best or shortest or longest. That will help you know what you're trying to optimize. Once you have that function, a lot of times that function will involve several quantities. But in Calc 1, we really only know how to optimize if there's one variable that's changing, the variable that we take the derivative with respect to. So you're also going to be on the lookout for constraints. So something that relates the variables that you could solve for one of the variables and substitute in order to reduce the number of variables involved in the quantity that you're trying to optimize. Then it's the usual find the critical points, places where the derivative is 0 or undefined, and check endpoints in the domain to figure out what your max is. So we'll work through several examples here. Here's one that's pretty just geometric. I'm going to read through the problem. You're planning to close off a corner of the first quadrant with a line segment 20 units long, running from some point A0 to some point 0B. Show that the area of the triangle enclosed by the segment is largest when A equals B. Okay, so we know we're talking about the first quadrant, so I'm going to draw the first quadrant. A point at AB would mean you go over A and you don't go out. A0 would mean you go over A and not up at all, and a point at B0 would be something like this. So a point where you don't go over, you just go straight up to B. And we're going to close off a corner of the first quadrant. So I got the first quadrant, and I can see, oh yeah, if I draw this segment, that's supposed to be 20 units long. I want to show that I get the biggest triangle when A and B are equal. So I got to think, I've got a picture and kind of see that if this length stays the same, then if I increase B, A is going to have to decrease, kind of like a ladder sliding down a wall in a way. Okay, and I'm just trying to figure out how do I change that so that I get the biggest possible triangle. Well, I know I'm trying to show that the area of the triangle enclosed by the segment is largest. I know I'm trying to optimize the area. Then that largest kind of set me off there. So I'm trying to optimize the area. Now the area of a triangle would be 1/2 the base times the height. And on this triangle, the base is this length, A. So we have 1/2 A, and the height is this length B. So 1/2 AB. The problem here, and it's a pretty typical problem, is that the thing we're trying to optimize, the area capital A, depends on two things, little a and little b. So what we're doing is looking for a constraint that relates A and B, and I can see that no matter where A and B are, this is the length that's 20 is going to be the hypotenuse of a right triangle. So I can see that when you take A squared plus B squared, that's the sum of the squares of the two shorter sides of a right triangle, that's got to turn out to be 20 squared. This is my constraint then, which will allow me to eliminate one of the variables in this problem. For example, I could solve for little a. That would be 20 squared minus b squared. So little a would be technically plus or minus, but we know it's in the first quadrant, so a has got to be positive. So the square root of 20 squared minus b squared. Let us substitute that in there, and now we have the area of the triangle as a function of a single variable b. We're going to have 1/2 and b and times a. I just rearranged it so the square root would come last. Alright, now there's a definite range of possibilities for b. B could go as high as 20, right? In which case a would be 0, and b could be as much as could go down to 0. If we go any lower, then we won't be in the first quadrant anymore. So we're going to have that relationship. So we have a function and its constraint. So since this is a continuous function on a closed bounded interval, we know that if there's going to be an absolute max and an absolute min, and it's going to occur at the end one of the endpoints or at a critical point in between. Now we see the endpoints certainly don't maximize area, because if b is 0, then there's no area. On the other hand, if b is 20, then a is 0, so we get this 20 squared minus 20 squared is 0 there, which wipes out the area. So we're pretty sure the max is going to be at a critical point in between. So let's calculate dA dB and see what we get. We'll have to use the product rule. We'll have 1/2 the derivative of the first times the second plus the first, that's 1/2 b. You take the derivative of this is something to the 1/2 power, so the 1/2 comes down. You get 20 squared minus b squared to the negative 1/2, and then you have to multiply by the derivative of what's inside, which is negative 2b. Let's see, so this 2 here cancels one of those 1/2s, and if I put them together with a common denominator, this one has a denominator that includes 2 and this square root, and I could get the same denominator if I multiply this top and bottom by that square root. So just getting a common denominator, the first term becomes 20b squared over 2 times the square root of 20 squared minus b squared, 20 squared minus b squared over 2 times the square root of 20 squared minus b squared, plus the other term here has a minus b squared. It's got b and b, minus b squared over 2 times the square root of 20 squared minus b squared. So put those together and we have 20 squared minus 2b squared over 2 times the square root of 20 squared minus b squared. Okay, since we know b has to be between 0 and 20 if we're going to be in the interior, we know that what's under the square root is always going to be okay, and it's not going to be 0 unless b is actually 0 or 20, or unless b actually is 20, which we're not going to allow. It's an endpoint where we already know there's a min there. So basically the only way this could be equal to 0 would be if the numerator was 0. So that would tell you that 20 squared equals 2b squared, or 400 equals 2b squared. So 200 equals b squared. So b is equal to the square root of 200, which is 10 root 2. Knowing that b is 10 root 2, we can substitute in to find a. So a would be the square root of 20 squared, which is 400. We know that b squared is 200. So a turns out to be the square root of 200, which is also 10 root 2. So we've shown that a equals b at our only critical point. Since the critical point has a non-zero area and the two endpoints both give 0 area, this must be where the max occurs, which is what we're supposed to show, that the maximum area occurred when a was equal to b.